Hello everyone, we are group 15 and for our final project we'd like to present our report on artificial pancreas and how it helps in early detection and prevention of diabetes. Now trust is something that backs up thriving healthcare organizations and any kind of failure in artificial intelligence, especially in the field of medicine, can completely erase the trust of public. For instance, a simple bias in an AI can lead to error-prone medical evaluation. Now, all these criteria would definitely sound familiar. To achieve the promise of artificial intelligence, the stakeholders must be ready to trust in their outputs. Now, the trust must be embedded in the core of the AI, and not only its surface. And this includes not only the essential steps in development, but it also includes the subsequent processes in the environment. It is majorly defined by the strategy, the culture, the mindset of the controls, and it also involves product management and also the technical skills of the developers. Now, this also is affected by external factors such as societal norms and values and regulatory environment and so on. Now, how exactly do you achieve this trust? So, the first step would be to strategize and set the business goals, set the values with proper infrastructure and governance. Next, you start building the system by identifying the scope, defining targets, and determining the basic architecture and functionalities, along with fairness and privacy concerns. Next, we integrate it with the concepts such as load balancing and providing security features like providing defenses against cyber attacks. And next, we assure, as in we verify and validate along the lines of performance, accuracy, transparency, and fairness. Now, as we all know, one of the most important factors of any relationship is trust. And the relationship between a diabetic person and their bionic pancreas is also built by trust. Now, for a person with diabetes, the artificial pancreatic system needs to inject confidence in the system's accuracy and consistency in order to achieve the proper result. And the task offered by the artificial pancreas is quite simple. But even though it's simple, the actual or the practical applications are quite complicated. Now, all these pancreatic devices use an insulin pump and a glucose sensor that senses continuously. Now, engineering human factors is also one of the most crucial parts of designing any system. And especially in the diabetic world, it is of key importance. And vital human factors such as the attitude of the patient, his or her emotion, their beliefs, and their expectations are overlooked. And because of this, the ability to trust the technology becomes a challenge. And all of these above mentioned factors become potential barriers. Now, let's start off by giving a brief introduction of what exactly the artificial pancreas do. Now, the artificial pancreas are something that mimic the functioning of healthy pancreas. Now, the healthy pancreas control the blood glucose level. People having type 1 diabetes are not capable of producing insulin. So, they control their glucose level in their body by ingesting this insulin manually or through an infusion pump. And this is done multiple times a day. Now, the AI pancreas automatically control and monitor the blood glucose level in the system, and they calculate how much amount of insulin is needed for the body at different parts of the day. Now, the continuous glucose monitor is a very crucial part of the artificial pancreatic system. What this exactly does is it tracks the blood glucose level every once in a while. It has a tiny sensor in it, and this is inserted under the skin. And what the sensor does is it sends the collected data to an app on a smartphone or the insulin pump. Now, this app evaluates how much quantity of insulin is actually needed for the body, and it instructs the insulin pump when the insulin is to be given to the body. And as for the insulin pump, um, the insulin infusion pump provides little amounts of insulin throughout the day. And when the blood glucose level is not at the desired level, this happens. We also have two different types of insulin pumps. One is worn outside the body, and the other one is attached to the skin. We have different types of artificial pancreatic systems, and here we classify them broadly into two. The first one is the insulin alone system, and the second one is the dual hormone system. So, when you talk about the insulin alone system, these systems keep the glucose level in blood in the desired range. They adjust the amount of insulin that needs to be delivered, and this is done automatically. Now, this is done based on one's CGM values, and they increase the insulin if the blood glucose level is higher than the targeted range. Now, there's another type called a hybrid system, which automatically manipulates the insulin level. But again, the person or the patient must still keep track of the carbohydrate levels and once in a while check the insulin doses for all the meals he or she consumes. The next one is the dual hormone system. They use two hormones. So, one is to reduce the insulin and reduce the blood glucose level, and the other one is called the glucagon, which increases the glucose level in the body. So, we have different mathematical models and different strategies that were used in the research for improving the design of the insulin delivery system. And we have several modern insulin pumps that continuously rely on software upgrades. And the safety related problems always remain concern. And they have also been analyzed in different publications because there have been instances of attacks targeting sensors.
Hello everyone, this is Neeraj Kumar. Let's look into the design factors of the artificial pancreas. To define the design factors of artificial pancreas, it is necessary to pinpoint its essential components such as medical goals, physiological factors, and subject difficulties and constraints. When it's come to the health objectives, the artificial pancreas design factors have to compulsorily satisfy the target audience as diabetic patients. Yeah, the objective of the artificial pancreas must be determined to fulfill the requirements of the target users. For instance, the infants who are diagnosed with type 1 diabetic called juvenile diabetic who are unable to control their insulin therapy and must be under parental control can benefits those children can be benefited from the artificial pancreas. However, because they are high risk category, the artificial pancreas will be subject to more strict safety regulations. On the other hand, a part of the physiological factors, the several consequences or outcomes of the improper human knowledge on how to control the diabetic. So, fully autonomous artificial pancreas that's needed no human input might be beneficial for people who experience a chronic hypoglycemia as a result of their failure to regularly and effectively monitoring low blood sugar. So here the hypoglycemia, a condition in which your blood sugar level is lower than the standard range, will cause all the horrible symptoms such as headache, hungry, sweat, so on, as is seen in this image. So moreover, the automated intelligent pancreas devices would decrease the number of hypoglycemia incidents. And secondly, reducing the amount of patient interference and help the patient to take care of themselves and also helps diagnose pre-diabetic conditions and prevent postprandial hypoglycemia as well. So especially the artificial pancreas is programmed in such a way that calculating the right insulin dosage to inject at right time intervals in the patient body. So here, an appropriate AI pancreas may be created with the help of several predefined design goals. This architecture depicts almost all the potential design combinations of AI pancreas working based on closed loop AI techniques. Yeah, let's have a brief description about the primary part of this pancreas model. So the first part, the intended blood glucose level, is the first choice that has to be mentioned. So this might be a constant value. Here the measured blood glucose is fed to the controller, who matches this measurement to the intended concentration of the human blood glucose. A prototype of the blood glucose could also be included in this algorithm. Yeah. Secondly, the various control algorithm has been tested and captured the different behaviors of the blood glucose level of the patient. So also implemented in this closed loop control system, such as fuzzy logic, a control model, a proportional integral derivative control. So these glucose prediction AI algorithms will be established to find the deviation from the determined target value of the glucose level and will produce the level of glucose aggression in the human blood. Yeah. The third main part of this architecture, this algorithm has been constructed in such a way that it produces an output for the supply of insulin and may additionally determine the delivery of other glucose regulatory hormones such as glucagon and pramlintide. Yeah. So the fourth part will sending all the actions that have to perform from the patient side, such as like a time to taking a meals, insulin, and so on. But this part is fully automated, so no input is required from the human. And the last one is sensor detection part. Your sensors such as heart rate, accelerometer, and skin temperature sensors collect the data from the human skin surface, and the false algorithm detect and process the signals received from these sensors, and this step will concurrently happen for every certain time interval before transmitting to the data signal to the controller. So this is the overall structure of this closed loop techniques architecture of the pancreas. Yeah, let's move on to the A pancreas integrated the A algorithms such as LGS and PLGS. So let's look into the two effective algorithms. So these algorithms are predecessor of closed loop algorithm. Yeah. So already integrated with the artificial pancreas and commercially available to help diabetic patient to maintain the proper glucose level in their blood. So these algorithms called the low glucose suspend technologies aims to prevent hypoglycemia by automatically stopping basal insulin delivery when measured blood glucose reaches a critically low level. Yeah, as you can see in this image, this LGS algorithm effectively controls blood glucose level by releasing insulin precisely. So there is a huge difference in the glucose level among artificial pancreas sensors runs with the LGS algorithm and without the LGS algorithm. So in this way, it helps improve the lifestyle of type 1 and type 2 diabetic patients. So next, the PLGS, the predictive low glucose suspend technology, which helps predict glucose level if goes below 80 mg within 30 minutes. Yeah, then automatically suspend the insulin injection. So it completely stops hypoglycemia and helps people to stop medication for hypoglycemia. Yeah. So here the FDA approved PLGS device made by the Tantum Diabetic Company along with the Dexcom G6 CGM machine, which means continuous glucose monitoring machine. So the basal IQ technology uses a linear regression algorithm that uses Dexcom G6 CGM the values to predict the glucose level 30 minutes ahead based on three of the last four consecutive CGM readings. If the glucose level is predicted to fall below 79 mg, the insulin delivery is suspended and the insulin delivery resumes as soon as sensor glucose values begins to rise. So insulin may be suspended for a minimum of 5 minutes and maximum 2 hours within 2.5 hours rolling window. So this is like well legitimate device available in the market for the people who have been diagnosed with type 1 and type 2. They can manage the blood glucose level very precisely. And let's move on to the, the existing wearable devices and types of the AI pancreas wearable devices available in the market. Oh, let's have some insights on existing wearable devices now. The first one, the diabetes assistant DIAs. Yeah, it's created by UVA. So University of the Virginia in 2011 was the first portable artificial pancreas platform. So DIA was created utilizing an Android smartphone as a central computing device. The users can keep monitoring their glucose level through this Android support user interface. So DIA's capacity to transition between the several operation modes according to the patient desires. So also provides support for prolonged graphical user interface and remote monitoring as well. So this would happen if continuous glucose monitoring signal were unavailable or if the patient not wearing that sensors device for certain amount of time. Yeah. Then like moving to the web server based AI pancreas blood glucose monitoring system can be easily accessed through the remote controller. Yeah, for remote monitoring, the desktop, laptop, tab or smartphone can be used to connect to the web server and fetch the display data to user understandable manner. Then the two primary wearable AI pancreas applications such as embedded system where insulin pump and CGM work by cloud service, and here the portable system that relies on the smartphone which communicate and command the insulin pump and CGM machines has been identified in the clinical studies and the clinical research sites in the United States including in France, Italy, Holland, Israel and Argentina. So although these structures have advantages and disadvantages, the last issue is whether the consumer electronics based artificial pancreas system might obtain FDA regulatory authorization, and this topic is now the focus of intense discussion on the many organizations who have been involved in the research and development of these AI intelligent medical implanted devices. Yeah. So thank you very much, and Tushi will continue the remaining part of the presentation. Thank you.
Thank you, Maladi, and thank you, Nurosh. So I'll be concluding the full paper and the drawback and obstacles in a closed-loop control system. The majority of the research rely on an insulin implantable devices and hypocalorimetric monitors that are readily accessible commercially and also constantly limited by their capabilities. For example, even though adding an additional sensor may increase the system reliability, but it overtake the weight to attach more sensors to the body for the usage of everyday life, and it will be a very difficult, and it might be a possible to create a contemporary sensors which are more compact and are made up of several sensors, enabling a duplicate blood glucose reading to work around the sensors issues. So the AP is mainly depend on the formulation of insulin, MLEs, and the prolamides that are presently in the market. While there have been studies into developing a better glucogens compositions, and also glucose is frequently challenging to work with the uh, it cannot be remain liquid. So the laptop, tablet, cell phones, or the other tiny computing devices that are readily available must be used to implement the systems. So in particular, if a connection is based on a wireless or Bluetooth type, so the battery capacity is a crucial consideration for these solutions. So as an existing commercial devices are used in the current AP design. This design must be relevant to the communication issues that may arise between the various hardware components. And also, they need to include the error in case of the issue is like a signal major distribution from the transmitting or integral sensor loss. So furthermore, existing system must show they can handle these issues throughout their validation space before being used in a clinical settings. Every one of these problems are indication of advancing technology, and also APS will be built using the combined gadget with the embedded control, which would do away with any communication cost and also the energy demands. So the view problems cannot be changed because they are a part of human physiology. For instance, once the insulin is injected into the body, it cannot be withdrawn. Therefore, control must be built to consider the insulin. Furthermore, insulin level might be very depending on the time, stress level, and the physical activities. Therefore, the control need to be in a reliance to this change. the future development of the artificial pancreas is the AP expansion is still facing several challenges. Before the AP device can be commercialized, there are several of these issues like continuous glucose monitoring, device accuracy, and insulin latency, and the effective communications among the part of the systems are being rectified. So the difficulties are especially the significant given like recent assertion shown on the AP by the US FDA administration, which is less similar problems as some other main obstacles in industrializations. So making a control assessment in the clinic would be a task in the upcoming years, but comparing the result over the various AP setups are due to the different protocol and provided data. So the primary rule issued by the FDA says that the artificial pancreas devices system described on the site do not involve biometrical, synthetic, and artificial tissues or organs. Has to be followed by all the research and the clinical trials, artificial pancreas, and gadgets. So therefore, it had been a tremendous stride made to the research and development of the artificial pancreas. So there on September 28, 2016, the FDA approved the first hybrid closed-loop system, which is Medtronic MiniMed 670G system external. So that shows the automatically monitored blood sugar and adjust the basal insulin dose in the people with the type 1 diabetics. So to conclude, the advance of the artificial pancreas technology is rapid. Since the beginning of the last 4 years, therefore, it has been more paper describing the clinical assessment of the AP gadgets. As an additional innovation, so move closer to the clinical experiment space, this quantity will rise considerably faster. And also the significant design concern for engineering must be taken into an account as the situations get much more complicated. So every clinical studies will provide an insight that can contribute to the common objective of creating an artificial pancreas to the increase the quality of healthcare if the protocol and guidance are disclosed measures for the organizations. And also we have attached a reference below. Thank you for listening.